Okay, we're going to solve the next exercise. Exercise is the number 1.27. The acceleration due to gravity on the surface of the moon is 1.62 meters per square seconds. The moon's radius is Rm, which is equal to 1,738 kilometers. See example 1.5. A. What is the weight in newtons on the surface of the moon of an object that has a mass of 10 kilograms? B. Using the approach described in example 1.5, determine the force exerted on this object by the gravity of the moon if the object is located 1,738 kilometers above the moon's surface. Alright, now, so I have right here that the acceleration due to gravity on the moon is equal to 1.62 meters per square seconds. The moon radius, which is Rm, is equal to 1,738 kilometers. And you're asking me for first the weight for when the object has a mass of 10 kilograms. And B, determine the force exerted. So I'm going to call that Fe. And then I have like an extra length of 1,738 kilograms. I'm sorry, kilometers. Now, what is the weight? So because of Newton's second law, which is force is equal to a mass multiplied by an acceleration, when we talk about gravitational forces, then I'll have that the force is equal to a weight, and that is equal to the mass multiplied by the gravity. So the weight is equal to the mass, 10 kilograms, multiplied by the gravity, which is 1.62 meters per square seconds, and the final answer is 10 times 1.62, 16.2 kilograms multiplied by meters per square seconds, or is the same thing as having Newton. Right now I've solved the first part of the exercise. Now the B part. Using the approach described in example 1.5, determine the force exerted on the object by the gravity of the moon if the object is located to that above the moon's surface. Alright, now there is a specific equation for when I want to know this force and this object is outside of the planet, or in this case the moon. So that equation is going to be equal to the weight, which is the same force as Fe, or the force exerted, is equal to the mass multiplied by the gravity multiplied by Re divided by R, the two of them evaluated to the second power. Then in this case, this Re is going to be equal to the radius of the moon, and this R is the distance between the two particles, in this case the center of the moon and the object. Now the force exerted is going to be equal to 10 kilograms multiplied by the gravity, 1.62 meters per square seconds, and multiplied by Re, 1,738 divided by 1,738 times 2. Why is that? Because this is telling me that this same length is going to be applied to the distance of the distance between the object and the and the center of the moon. Let me like put it much more graphical here. So here I have the moon, here I have the radius of the moon, which is 1738, and here I have the particle, which is 1738. So this whole length is equal to 1738 times 2, evaluated to the second power. Now, times 1738 times 2 to the second power. This is equal to 4.05 newtons. Why is that? Because here I have kilometers, here I have kilometers that are going to be eliminated because of the division, and here I have kilograms multiplied by meters divided by square seconds, so this is the same thing as having a newton. Now that I've explained, or that I've solved the exercise, I wanna explain the physics behind this exercise and the physics that are needed to be understood to solve it. Now, when I have two particles, one right here and one right here, separated by a distance that I'm going to call r, and I'm going to call the mass of the first particle m1 and the mass of the second particle m2, there is going to be generated a force between them that is going to be the same for the two of them, actually. And that force, Isaac Newton said actually that force is going to be equal to a constant g multiplied by the m1 multiplied by m2 divided by the distance between them to the second power. Now, this F is a force, so a force is given by a mass multiplied by an acceleration. So a mass multiplied by acceleration is equal to g multiplied by m1 multiplied by m2 divided by r to the second power. Now, because we are talking about a gravitational force, and on the surface of the moon, if I have a particle that this is going to be the mass of the particle, and this is going to be the mass of the particle as well. So I could send this m to divide the other part of the equation, and I could cancel these two, this value from the both sides of the equations. So I'll have a equal to g multiplied by m2 divided by r to the second power, in which this m2 is the same thing as the mass of the planet or the moon or whatever. Now that I've explained this g, because it's a constant in international system units, is going to be equal to 6.67 times 10 to the minus 11, and this is the important part, newtons multiplied by meters to the second power divided by kilograms to the second power. Now I'm going to multiply by the mass, so I'll have right here kilograms. Now, because of this, I could transform the the upper side of the division into this. In which this RE is the same thing as having the radius of the planet or the Earth evaluated to the second power, and this G is the same thing as the gravitational acceleration of the planet or the moon. Now, let me explain why this is equal. Actually, let me explain why this is the same thing. Now, Newton meter square, kilogram square, kilogram is equal to meter per square seconds multiplied by m meters to the second power. So this part of the equation refers to this part, and this part of the equation refers to this one, because the gravity and the radius. So developing the equation, I'll have right here meters to the third power divided by square seconds, and if I play with these units, I'll have the same thing. So let me show you. If I cancel these kilograms with these two, and okay, let me put it like more understandable. So a Newton is equal to a mass multiplied by an acceleration, because a Newton is a force. So a mass is a kilogram and the acceleration is equal to meters per square second. So I'll just rewrite the same units. Right here I could eliminate, I'm sorry, I just forget these kilograms, these ones. And right here I could eliminate these kilograms with these kilograms, actually these kilograms with these 2 kilograms, and these kilograms with these kilograms, and the answer will be meters to the third power divided by square seconds, which is the same thing as having this. Now this G is I have to write down TR to the second power. And this is closer to the equation that I used to solve the exercise. I just gotta multiply both sides of the equation by the mass. So by the mass and by the mass. A mass multiplied by an acceleration is equal to a force, in this case the weight. Now a mass multiplied by the gravity is the mass multiplied by the gravity. It's also a weight, but we're going to put it on those terms, the mass multiplied by the gravity. So the weight is equal to the mass multiplied by the gravity multiplied by RE, which is the radius of the planet or the Earth or the moon or whatever, divided by the distance between the object and the center of the planet, and both of them evaluated to the second power. So this is the same thing as this. Alright, now guys, this is how this exercise could be solved.